Okay, welcome to Power Series. One thing we're going to have to do quite a bit is take an expression in an absolute value and set it less than 1 and solve for x. And so I just want to review this with you. The way to get rid of the absolute value when you have the absolute value of a is less than 1 is to set a less than 1 and greater than negative 1 and then solve. If our a is x minus 2 over 3, we want to set that less than 1 and greater than negative 1. You cannot work inside an absolute value. So the very first step is to get rid of the absolute value by doing this. Then you can use the rules of inequalities. Like you can multiply all three sections by 3 to get negative 3 less than x minus 2 less than 3. And finally, add 2 to all three sections. So negative 1 less than x less than 5. There's your inequality. All right, a power series is an infinitely long polynomial. A power series is centered at a if it has this form. And a special case is if a is 0, then it just looks like the sum of cn x to the n because the minus a part is 0. So this power series here is centered at 0. This one's centered at negative 1 because you have to write x plus 1 as x minus negative 1, and this one is centered at x equals 2. A power series will always converge in at least one place, and that's where it's centered. We're more interested in finding out all the set of x's for which the power series converges, and that's called the interval of convergence. So it's the set of all x for which the power series converges. I use IOC as my shortcut. The radius of convergence is half the width of the IOC. So for example, if the interval of convergence goes from negative 3 to 3, that interval has width 6. Half that width is 3. That's the radius of convergence. Okay, and then we have a theorem that tells us what kind of interval of convergences are possible. There's 3 possibilities for a power series centered at 0. You can generalize to power series centered at a. The worst case scenario is that the power series only converges at 0. And so that will be a single point. The best case scenario is the power series converges everywhere. That's over here, all x. And then the most common one is the power series will converge in a symmetric interval around where it's centered, like from negative r to r. It will converge absolutely for all the x's in there, and then you don't know what happens at the endpoints. And so one of our jobs today is to figure out what happens at those endpoints. Let's go through and see how to find a radius of convergence. We're going to use the ratio test to find rho. And remember the rule for the ratio test. For convergence, you need rho less than 1. So we're going to take the absolute value of the an plus 1 over an, and then take the limit as n goes to infinity. So this is limit as n goes to infinity, absolute value of n plus 1, x minus 2 to the n plus 1 over 3 to the n plus 1. And then instead of dividing by the nth term, I'm going to multiply by the reciprocal of the nth term. So 3 to the n, x minus 2 to the n. Okay, so now remember n is positive. So the only thing that's going to have an absolute value on it is the expression involving x, because that's what we don't know, whether that's positive or negative. So I'm going to clean this up. The limit as n goes to infinity. Let's group like terms. Okay, I'm going to put the n plus 1 over the n. I'm going to put the 3 to the n over the 3 to the n plus 1, and I'm going to put the x minus 2 to the n plus 1 over x minus 2 to the n. You could do this step mentally. Limit n goes to infinity. Now I'm going to take the absolute value off of these two pieces. N plus 1 over n is 1 plus 1 over n. I'm going to write that as two fractions. 3 to the n over 3 to the n plus 1 is a third. Then x minus 2 to the n plus 1 over x minus 2 to the n is x minus 2 to the 1. But I don't know whether that's positive or negative, so that has to have the absolute value on it. So see this note here. Can't remove absolute value from the x minus a piece. Okay, now take the limit. Remember, the limit's on n, not on x. So this This guy goes to 0. 1 is 1. A third is a third. That just sits there. So I'm going to drop the limit. The only things left is 1/3 absolute x minus 2. That's rho. Step 2, set rho less than 1. That's what we need for convergence. So that would be 1/3 x minus 2 absolute value less than 1. Isolate the absolute value, so multiply both sides by 3. And now to remove the absolute value, you have to use that rule. So this means that implies -3 less than x minus 2 less than 3. That's how you remove the absolute value. And now add 2 to all three sections. -1 less than x less than 5. All right, that is an interval of width 6. So radius of convergence is 3, all right? Here are the possible IOCs. We could have convergence at the two endpoints, in which case we'd have this guy. We could have divergence at both endpoints, in which case we'd have this guy. We could have divergent on the left, convergent on the right, or convergent on the left, divergent on the right. Those are the possibilities. And in the next example, we're going to see how to test the endpoints to see which one we get. But for this problem, we were just finding the radius. So we're done at this point. Some of your homework problems say find the radius. Some say find the interval of convergence. And so I have a flow chart, of course. This is for a power series centered at 0, but you can generalize it for one centered not at 0. Use the root or ratio test to find rho, and then typically you're going to set rho less than 1. We're going to do that on the next page. But in these first two examples above this flow chart, I'm going to show you what happens in the special cases where either rho is 0 or rho is infinity. So let's take a look at those. Find R in the IOC by using the ratio test. Okay, here we go. Rho equals limit n goes to infinity, absolute value. I'm going to take an plus 1, divide by an. X to the n plus 1 over n plus 1 minus 1 would be n factorial, 2 to the n plus 1. I'm going to multiply that by the reciprocal of the nth term, n minus 1 factorial, 2 to the n over x to the n. Limit n goes to infinity. I'm going to group like terms. I'm going to put n minus 1 factorial over n factorial. I'm going to put 2 to the n over 2 to the n plus 1. And I'm going to put x to the n plus 1 over x to the n. That's limit n goes to infinity. Now this step you could do mentally. I have no trouble with you writing it down if you want, but I also have no trouble with you going straight from this first equality to 1 over n, and then 2 to the n over 2 to the n plus 1 is a half, and I'm taking the absolute value off of those because I know they're positive, and then the only thing that has to have the absolute value on it is the term involving x, and that will just be x, because after you simplify that, you just get x. Now let's take the limit. Remember, the limit's on n. X is just some number sitting there. So this is 1 over infinity times some fixed number. So we get 0, all right? Or if I can make it more explicit if you want, this is absolute value of x over 2 times infinity, which is 0 for any x. And so 0 is always less than 1. Remember, that's the rule for the ratio test. You need rho to be less than 1. Well, 0 is less than 1 for any x. So the radius of convergence is infinity, and the IOC is all x. And in my flow chart, that is here, this side, the left. And it's funny because the numbers switch. If rho is 0, the radius is infinity. And in the next example, we'll see if rho is infinity, r is 0. So just keep that in mind. There's like a flip there. Okay, so the next one, we should get rho equals infinity. Rho is the limit as n goes to infinity of the absolute value. Now, since this is not a fraction, I'm just going to put the nth plus 1 term over the nth term. I got so excited I spit on my screen there, and now I'm having trouble with my pen. Okay, n factorial. That's probably more information than you wanted. X minus 3 to the n. Okay, and so that's the limit as n goes to infinity, n plus 1. That's positive. And then I want to leave the absolute value on the x minus 3. Okay, so make sure you follow that. Now, that's going to be infinity times the absolute value of x minus 3, which will be infinity unless, remember, a power series always converges in one place, and that's where it's centered. So unless x is 3. If x is 3, that will be 0. But in every other case, that limit's going to be infinity. And so in my flow chart, when rho is infinity, your radius is 0 and your IOC is 0, but that's for a power series centered at 0. If it's centered at A, your IOC will be A, but the radius will still be 0. Okay, so let me explain that. So up in this situation here, we do have convergence at 3, so that means our IOC is the single number 3. That is an interval of width 0, so the radius is still 0. It's just the IOC isn't 0, it's 3, because that's where the power series was centered. It's a little confusing, I know, but you'll get it. And now the most exciting case is this middle case, and we've already seen what happens there in the first example, right? We got a certain set of x's for which the series converged, and then we didn't know about the endpoints. So now we're going to do an example where we check the endpoints. And so looking at our flow chart here, in the middle example, you set rho less than 1, you solve for x. In the previous example, we got x between -1 and 5, and then you actually have to check the endpoints by hand by plugging them into the original power series. So that's what we're going to do in this next example. Okay, so find the IOC and R. So these all start the same way. Rho is the limit as n goes to infinity, absolute value of the nth plus 1 term divided by the nth term, 3 to the n plus 1. And instead of dividing by the nth term, I'm going to multiply by the reciprocal, n, 3 to the n over x to the n. That's limit as n goes to infinity. I'm going to do two things at once. I'm going to group like terms, and I'm going to take the absolute value off of stuff that doesn't involve x. So 3 to the n over 3 to the n plus 1 is a third. And then the only thing left that needs to be in the absolute value is the x. Okay, now this is infinity over infinity. So I need to divide top and bottom by n. We all know the answer is 1, but I want to see that you know how to do it. So I get 1 over 1 plus 1 over n times a third times the absolute value of x. Now I can take the limit. This will be 1, so I'll get the absolute value of x over 3. So that's step 1. Now I want to set, I'll call this step 2, set rho less than 1. I don't care if you number your steps. I'm kind of big on steps. I try and make it more manageable that way, like bite-sized pieces, but for some people, it just, they don't want all those numbers. Here we go, rho less than 1. So that's going to give us absolute value of x over 3 less than 1. Multiply both sides by 3 to isolate the absolute value of x. And now to remove that absolute value, you make a sandwich. You sandwich x between 3 and -3. Okay, we now know our radius of convergence. So if the problem were just to find the radius of convergence, we could quit. R is 3, because that's the width of that interval is 6. Half of that is 3. So our possible IOCs are -3 to 3, open on both sides, closed on both sides, open on the left, closed on the right, or closed on the left, open on the right. We're at this point in the flow chart. Check the endpoints to determine which one you have. So you take the endpoints and you literally plug them back in to the original power series and use whatever test is appropriate to determine convergence. So 3, we're going to test our endpoints. And when you test your endpoints, for me anyway, I want you to write down which one you're testing so I can follow your work. So we're going to have to test x equals -3 and x equals 3. I don't care which one you test first. I usually test the left one first because it's on the left, but write down what you're testing. And then go back to your power series, which is off the page here. Our power series will be 1 to infinity. I'm replacing x with -3. So I have to use parentheses. -3 to the n over n times 3 to the n. I have to decide whether that converges or diverges. So the first thing I'm going to do is clean it up. N equals 1 to infinity. So -1 to the n times 3 to the n is the same as -3 all to the n. What that allows me to do is cancel the 3 to the n's. Sweet. So now what I have is the alternating harmonic series, okay? And I know that converges, but I'm going to show it anyway. But here's how you would show it. You're going to use AST, alternating series test, with UN equal 1 over n, because this is the same as the sum of -1 to the n, and then 1 over n is the positive sequence UN. So there's 3 conditions. 1, I'm going to write really small. 1, limit as n goes to infinity of 1 over n is 0. Check, nothing to show. 2, 1 over n is positive for all n. Check, nothing to show. 3, do you guys remember the third condition? I do. It's that the sequence 1 over n has to be decreasing. Numerator's fixed, denominator's increasing, that's a check. So we have convergence at x equals -3. That means this guy's out and that guy's out. It's going to have to be this one or this one for the IOC, because -3 is part of the interval of convergence. All right, so now let's check the other endpoint, x equal 3. Then we get sum n equals 1 to infinity of, remember what the original guy was, x to the n over n 3 to the n. So 3 to the n over n 3 to the n. Now this is much easier. Kill, kill, 1 to infinity, 1 over n. This is a divergent P series because P is 1. So this guy's out. So our IOC is -3 to 3, including the -3, but not including the 3. And so that's how you do an interval of convergence from top to bottom. Okay, so let's talk more about the endpoints. So here's an example where we're just going to talk about the endpoint. Suppose you're testing the endpoint x equal -2 for this power series. What test would you use to determine if the series converges or diverges? So you've gone all the way through the steps. You've found the radius of convergence. You've found possible IOC. And this is one of your endpoints. So let's see what happens. We're going to plug x equal -2 into that series. So we get the sum, n equal 1 to infinity, -1 to the n. If x is -2, -2 plus 1 is -1, and that's to the n. And this will be over n plus 1. Okay, and so that's -1 to the 2n over n plus 1. But -1 to the 2n, think about it, 2n is 2, 4, 6, 8. So the numerator is always positive. That's just always 1. The numerator is always 1. So this is the sum, n equals 1 to infinity of 1 over n plus 1. All right, and so if I know that diverges, because it looks like the harmonic series, which diverges, a direct comparison kind of goes the wrong direction. So I would use limit comparison with the sum, n equals 1 to infinity of 1 over n. All right, and I'm actually going to do it just to remind you how limit comparison works. Let's just show that this guy diverges because of limit comparison with that series. So remember, limit comparison, you use the number L. L is the limit as n goes to infinity of your given terms divided by the terms that you're comparing it with. But I'm going to multiply by the reciprocal of the terms I'm comparing it with to skip a step. Now that's infinity over infinity. So I have to divide top and bottom by the highest power in the denominator, 1 over 1 plus 1 over n. So that's 1. Significance of 1 is that it is not 0 and it's not infinity. So that means my series will do whatever the series I compared it with does. So limit comparison with 1 over n shows that the series diverges at that endpoint x equal -2. So that would not be part of the interval of convergence. Okay, same question, except now you're going to test the endpoint x equals 0. So let's see what happens. If we put in 0, then we get sum n, this will be a little quicker, the sum n equal 1 to infinity, -1 to the n times 1 to the n, but 1 to the n is just 1. So I'm not even going to write 1 to the n. I'm not even going to write 1. I'm just going to write -1 to the n. That's this guy. Well, I'll write the 1. Okay, 1 over n plus 1. All right. And so that, it's an alternating series. So I'm going to use AST with my un equal to 1 over n plus 1. And we're going to get converges because the three conditions are 1, the limit as n goes to infinity of 1 over n plus 1 is 0. Check, nothing to show. 2, 1 over n plus 1 is positive. Check. 3, the sequence 1 over n plus 1 is decreasing. Check, nothing to show. So we have converges at x equal 0. Now we're going to find the radius of convergence for this same power series. And I say do not test the endpoints because we just did. We already tested the endpoints. So from our work above, we had divergence at -2 and convergence at 0. So we're going to see that our interval of convergence is -2 to 0, not including -2, but including 0. So I'm just going to go through how to find the radius of convergence with you. You already know how, but we're just going to do this one together anyway. And I've started us out. So this is, all right, I'll just go slow. Limit n goes to infinity, -1 to the n plus 1 over -1 to the n is just -1, okay? We're going to have the absolute value of that times the absolute value of n plus 1 over n plus 2 times the absolute value of x plus 1 to the n plus 1 over x plus 1 to the n. And so I just wanted to do that for you so you could see what's happening here. This is the absolute value, these negatives, of -1, which is just 1. So this guy is just going to completely disappear. In fact, I'm going to erase this. And this is already positive, so it comes out of the absolute value. And then this guy does have to stay in absolute value. And if you simplify, you just get x plus 1 to the 1. Okay, so that's infinity over infinity. So we need to divide top and bottom by the highest power in the denominator, which is n. So 1 plus 1 over n, 1 plus 2 over n. Absolute value of x plus 1. Now I take the limit, and I just get absolute value of x plus 1. So that's my row. And then I want to set row less than 1 to get my interval. So I'm going to solve absolute value of x plus 1 less than 1. Okay, to remove the absolute value, you make a sandwich. This implies -1 less than x plus 1 less than 1. And now subtract 1 from all three sections. -2 less than x less than 0. That's an interval of width 2. So my radius is 2. And that's how I got those points in the previous, in A and B. I said test this endpoint and that endpoint. This is how I got those numbers to test. I had already done this calculation in my head, and I knew that those were the two endpoints I would have to check. So if you were doing this problem in real life, you would have done C first, C, and then you would have done A and B to check your endpoint. Okay, and that is it for this section.